Okay. Hi, everyone. Welcome to today's live streaming. We're going to wait just a couple of minutes and then we start. Okay, hello everyone, and welcome to today's Twitch session, Hazelcast Platform versus Apache Flink. My name is Chiara, and I will be the host today. The session will be led by Christoph Jamrus, Senior Software Engineer and SQL Team Lead at Hazelcast. If you have any questions, please type them into the chat box, and we will answer as many as we can at the end of the session. But let's get started now. Christoph, can you tell us where you're based and what you're working on right now?
Hi, everybody. My name is Krzysztof Jamrus. I work for Hazelcast for a year. I'm senior software engineer. I'm a team leader in SQL team, which develops our stream processing and SQL language features. I'm based in Poland, near Warsaw, in a small city near Warsaw. Today I will talk about comparison between the Hazelcast platform and Apache Flink. It's a huge topic, so it won't be a complete comparison, but I'd like to talk about a few things that Hazelcast and Flink have in common, and also about some differences when it comes to stream processing and how does it work. So the plan for today is first to talk a bit about the architecture and how the stream processing works in general, and about similarities. And then we will talk about the data, where you can store the data, where you store state of the jobs, and how you deploy your streaming jobs. And at the end, I will answer some questions. Okay, so let's start with a bird's eye view on the architecture of stream processing in general. This diagram shows this similarity between Hazelcast and Flink. On the lowest level, stream processing in Hazelcast and in Flink is implemented as a directed acyclic graph. So that's the representation that underpins all other APIs and abstractions. And the DAG, the directed acyclic graph, defines nodes or vertices which do some processing, and edges which describe where the data flows from and to. So it flows from one processing node to another, and that's the basis of all features of stream processing. So a job defined that way can be scaled if we run multiple instances of the processes processors. It can be distributed. Also important thing is fault tolerance and processing guarantees. So in case of failure, you don't want your job to lose state or lose some messages that were processed by the job. This is implemented by a clever process of snapshotting or checkpointing in Flink's as Flink names it, where we capture a consistent snapshot of state of all the processors in the DAG. And this works in a very similar way in Hazelcast and Flink. This is a very similar algorithm. And thanks to that, we can provide fault tolerance and exactly once or at least once processing guarantees. So you don't have duplicates or don't lose any messages. But this lowest level API is rather complex to use. But it's available. It's both in Hazelcast and in Flink. It's an internal API, but if you really want, you can use it. It's the most powerful API, but the most complex one. So it makes sense to have some more convenient abstraction on top of that. And in case of Hazelcast, we have a pipeline API. Flink has a data stream API, which provide much more convenient API for creating a stream in a more natural way. So you tell the system that read from this topic, then do some processing, do some aggregation, everything in a fluent API. So it's convenient, and you can express the transformation aggregation logic in a short and understandable way. But under the hood, these APIs are translated to DAG for execution. Also, we have even higher levels of the API. So instead of building your queries using some more or less but specific API for the streaming, Flink provides also a table API, which is Java API, which feels a lot of like SQL language, but you write your queries in Java. If you used some libraries for generating SQL queries in Java, like query DSL, it feels very similar. And the most higher level abstraction is SQL. So you can actually query your streams, aggregate the data, read from sources, and write to things using SQL, mostly standard SQL with some extensions which are specific to the nature of stream processing. But also with SQL you can transform batch sources, not streaming sources, but batch data in the same language, in the same framework. Both Hazelcast and Flink give quite powerful SQL language for stream and for batch processing. Yes, and also recently it's very popular to do some machine learning, artificial intelligence, and for that Python is quite often the language of choice. So it's important for the streaming products to be easy usable from Python. And Hazelcast can be easily used for Python from Python. We have a client in Python. Flink also can be used from Python via PyFlink integration. So actually the Flink integration is a bit more powerful because you even can create your streaming jobs in Python. Currently in Hazelcast, you need to create your jobs in Java or in SQL. But apart from that, you can use both products from Python in a convenient way. So yes, that's the very high level overview. I would add that Hazelcast is more than streaming, which we will be talking about later. That is only the part related to strictly to streaming. Before we talk about the differences, I'd like to introduce the example. So for the sake of example, let's think about fraud management, fraud detection, fraud management application that analyzes incoming transactions and checks if they are fraud or they are okay. And there are usually such systems implement some rules or some patterns and decide which pattern is fine and which pattern is suspicious or straight or just fraud. Yes, and for that, first we need to have some data because data that are in the event, like for example the transaction only, are not sufficient to interpret the transaction, because it's different if a transaction is for $10,000 is made by the user whose debit card who uses debit card and it has only $10,000 limit, and it's different if the same transaction is made by a VIP customer with a very high spending limit and prestigious credit card. So we need such context in order to be able to meaningfully interpret the data in which is coming through the stream. In Hazelcast, we can use built-in data structures that Hazelcast supports. For example, IMAP, cache or list or topic, in order to get some contextual data. And they are embedded. They are very convenient to access, and they are very fast because they are just handy in the same cluster even as the stream processing happens. But also you can use external data stores like JDBC database, Elasticsearch, or MongoDB. You can also get data from that. You have choice. In case of Flink, traditionally, Flink focused on the processing itself, and the data was stored outside. So you had to use JDBC to connect to database, Redis, or other ways of storing the data outside Flink, which increases the complexity. It's also additional request to get data needed to enrich your stream. Recently, Flink is working on Flink table store, which will embed some storage directly in the Flink cluster, but this is still work in progress. Okay, so after we know what is the customer, what is his credit limit, is it a VIP customer or a normal customer, we need also to track some patterns in time because they are also very indicative of for frauds. And for that, we need to keep state, because we don't only work on a single event level, but we need to aggregate the data from many levels. Like, for example, amount of money spent during given day or a week, or, for example, geographical localizations and how far apart are they given time between the transactions. If they are in very distant places and the transactions take place like in 5 seconds or a few minutes apart, that's very suspicious. But in order to track that, we need to have some state that is kept and updated with the incoming events. And Hazelcast and Flink deal with that. This is one of the major features of stream processing products in general. So in case of Hazelcast, we store such state like partially aggregated values, like some of the transactions in native format in Java on the heap. So it's very fast to access. It's very fast to update when new events come. But that's one side of the coin. But we also need to make snapshots or checkpoints in Flink to provide processing guarantees and fault tolerance. So when doing snapshots, Hazelcast needs to serialize all those data that are kept as part of state in memory and we'll put them in IMAPs. So again, we're using the data structure Hazelcast already has, which is very performant, replicated, fault tolerant, and very well tested. So we can reuse that. Snapshots are stored in the cluster as well. In case of Flink, Flink has two options to keep the state. One is using RocksDB, which gives the ability to keep the data on disk also. But for that, the price for that is that the data have to be serialized when they are updated. So each update needs to serialize data, read will deserialize them. That's the price. But on the other hand, it gives you faster checkpoints, because you already have all the data in the RocksDB files. That you only need to make sure that the files are consistent and cut off them in some point. So it may be much faster than writing entire snapshot from scratch. Another option in Flink is pure memory backend for storing state, which is based on hashmap, and that should be quite similar to what Hazelcast has. Okay. When we have our job, it works. It knows its data. It keeps some snapshots, state, etc. We need to deploy the job to some production environment, and Hazelcast gives you a choice how you want to deploy it. You can use Hazelcast as embedded library, so put it alongside your application in the same process as the application, if it's of course running on the JVM. But still, this embedded instance will be a full-fledged cluster, so it can connect with other instances. You can connect them in the cluster. So it will work. It will work as a full cluster with all features. You can also run Hazelcast as a standalone standalone cluster, and clients may connect to that. Or you can run Hazelcast in the cloud, in the Kubernetes cloud, or you can use our managed cloud Viridian. So there are lots of options, but they are very similar or practically the same from the client's point of view. So it doesn't matter if it's embedded or cloud or managed cloud. You use it in practically the same way. The only difference is, of course, the connection details, how you connect to the cluster. But apart from that, you use it in the same way. Also, Hazelcast is a single integrated library or product. So you have everything in one package. You have stream processing, you have storage, clustering, also some management capabilities. Everything is integrated, and we can leverage the features in one component in another component. Comparing that to Flink, when running Flink, you need to configure a few components. You have Flink itself, but also RocksDB if you use it. You have to keep, if you want to keep your data somewhere, you need to configure a database. In Hazelcast, might be not necessary. Also, you need to configure a place where you store your checkpoints. So there are many more moving parts that have to be chosen and configured, integrated, and tested if they work together. Flink also, because it's popular, there are also many providers for managed services for Flink, which make it a bit easier to start with that configuration. But yeah, I think that Hazelcast gives you here a bigger flexibility, and also it's still easier to use. Also, you can use Hazelcast. You can embed Hazelcast anywhere in your architecture. So it doesn't have to completely. You don't have to completely revamp your architecture to leverage real-time data streaming. It can be added to existing existing infrastructure. Okay, so that was very short comparison. Of course, it's not exhaustive. There are many more aspects that need to be taken into account when choosing which solution works best for given case. But that's some. I think that's some starting point.
Thank you so much, Christoph. We do have one question, actually. Is it better to use SQL or Java APIs to create stream processing jobs?
Yeah, so that's a kind of question where it depends. So both Java APIs and SQL have their advantages and disadvantages. Java API is the older one. It was available earlier, so it's more mature. It may have more features that are available in SQL. But you're limited to Java or JVM languages. On the other hand, SQL may be familiar also to users that don't know Java, but users that analyze data usually know SQL can use it straight away. Also, SQL gives you it's even more concise and even more powerful than the pipeline API because of the nature of SQL. SQL is designed to query data, to do some aggregations, joins. So it's very convenient in SQL to do that. But it's also another layer of abstraction, and it adds some complexity. But maybe worth of it. So it depends, but I think I would usually start with SQL and only revert to Java API if something cannot be done in SQL, or if there are some other considerations that rule SQL out. But I think SQL is the more convenient API for that.
Thank you so much, Christoph, for a great session. And thank you, everyone, for joining us today. We hope you enjoyed it. Make sure to join our community on Slack, on Twitch, and our community newsletter as well. Thanks again, and have a great rest of your day.
Thank you.